Hi everyone, I'm Evgenia.
I'm Dima.
And today we are presenting the results of our project, a comparative analysis for explainable AI method package. This project is a collaborative effort involving our inspiring mentor Maya Malamud and supportive companies representative Rana Moon and Dagana Shar. The company is called Citrus, and it developed a platform for AI transparency and explainability. In other words, it explains model decisions in a user-friendly manner. But who needs to understand this decision? Imagine encountering a decision that affects you directly, whether it is a medical diagnosis, a job application rejection, or a loan refusal. Clearly, the question why becomes significant. But let's say if your loan application was rejected and in the meantime you got a clear explanation about the decision-making factors and you would know what you can change to change the model decision, surely your trust in the decision-making process will increase. So besides regular customers, data scientists need to understand how models make their decision to improve their outcomes, and business decision makers need to understand it to be sure that these models align with the company's strategic goals. So there is a set of processes and methods that provide human understandable explanation, and this domain is called explainable AI. The groups in this, the methods in this domain could be grouped. First, there is a group of simple models that are interpretable by design, like decision tree and logistic regression. Secondly, there is a group of model intrinsic methods that are tailored for a specific type of models, like explainable boosting machine for gradient boosting models. And third, there is a group of model agnostic methods that could be applied to various types of models. And we were focused on this group within our project, and specifically on SHAP, LIME, and permutation feature importance methods. But now let's look at our goals.
Our goals was ambitious yet straightforward. We were going to create a Python package capable to compare different explainable AI methods based on two key techniques: feature selection and consistency measurement. We will cover it later in our presentation. And now let's get to our results. We succeeded. We created a Python package. Look at this beautiful logo and structure of the package on the left side of the screen. It is pip installable. This means that you can easily type pip install xai compare, and our package will be straight on your computer, like pandas on NumPy, ready to use. Let's go back to explainable AI methods. We used model agnostic methods, commonly called explainers. They look at machine learning model like a black box and uses only a prediction function. And we use this LIME, SHAP, and permutations, and you can, with our package, choose the best one for you, for your case. First one is LIME. LIME is local interpretable model agnostic explanations. Imagine a similar case, you have two classes, two features, and this is a visualization of the decision boundary of your model. LIME helps you to understand this particular point. It creates different instances around your point and ask the model to give a prediction for each one. And for those who are closer to the original instance, it gives more weight. And after that creates a similar linear model, which are interpretable and explains your model in this particular area around this data point. Another one is SHAP. SHAP uses game theory. Imagine you have a team, and team who won a prize, and you need fairly distribute this prize between all the members of the team. How to do it? Calculate Sharp values. What does it mean? Sharp considers all possible combinations of the features or the persons and calculates contribution of each person to the prediction, to the result.
And the third wrapper we created is for permutation feature importance. This technique is pretty simple and straightforward. You take the model and train it with the original dataset and evaluate the model performance. Then you choose one feature and you shuffle the data within this feature. And then you evaluate the model again. And if the model performance drops significantly, it means that this feature is important. And if the model performance doesn't change much, it means that this is not an important feature. And you do it for all the features in the datasets. Then we created an explainer factory. This factory helps us to create explainers within just one line of code. And this is central for our comparison part of our package. So as you saw, there are a lot of different explainers. So how can you choose the explainer which suits for your goal? So you can compare explainers based on their computation time and fairness and stability. But in our project, we were focused on the feature selection and consistency. So let's start with feature selection. Feature selection, this method helps to compare different explainers, not by the ability to choose the best feature set, but besides it, it also reduces the model complexity and potentially even enhances its performance. So let me walk you through it to explain how it works. The input to this module are a dataset, a model, and an explainer. So at first, it takes a dataset, train the model, and evaluate the model. And this is how evaluation looks like for classification and for regression problem. Then it stores those evaluations because we will need them later. Then it get explanation using the given explainer. And this is how explanation looks like. So basically, this is just feature importance. And based on this explanation, it choose the least important feature and then eliminate it. And this loops repeat until the number of features in the current dataset reach the established threshold. And when it's happened, the module chooses the best feature set based on the highest value of the target metric in the evaluations which we stored earlier. And the target metric also could be specified. So then it evaluates the best feature set based on the test set, and that is how we get the result for one explainer. And this process replicated for each explainer. And here you see how the model metrics change during the feature elimination process. And eventually, it creates a report that showing the best feature set per each explainer and comparing the metrics for the model across the different test sets with those selected features and the original feature set.
Also, with our package, you can compare consistency of explainers. It means that to compare their ability to yield similar explanations for similar cases. Let's break down how we evaluate it. We start with the model and the data set. Then we train the model. Our test set we split into, say, 3 folds. We create explainers to evaluate the consistency for each fold, and each fold with the trained model, we apply explainers on them. And after that, we extract the explanations. We got a feature importance for each fold. After that, we calculate standard deviation between them, and this is how we evaluate the consistency. Very simple. You can see our results. If you need, for your case, for your particular data set and your model, choose the best one explainer, you will choose Sharp here because it has minimal standard deviation. Also, same like for explainer, we created a comparison factory with one line of code. You can run and apply different comparison techniques. Also, we provide documentation, how to install, how to use our package. And we used it in our MLOps project.
Yeah, we had this opportunity. So the project, in this project, we were given a dataset, a model, and the goal of this project was to create an MLOps pipeline and enhance the model performance within this pipeline without changing its model, without changing model's hyperparameters. So we decided to use our package. Basically, we integrated the feature selection class in our pipeline and provided their model, dataset, and we specified our target metric. And eventually, it increases the model performance by given metric by 12% for given metrics. And we encourage you to try to use our package in your future ML machine learning projects. As you saw, it can enhance your model performance and help you to choose the best explainer for your goal. And also, our package provides a framework to create your own explainer and your own comparison technique. And given the increasing implementation of AI everywhere and demand for its explainability, we believe that our package could be a valuable tool for the data science community. And there are still a lot of things that could be done to improve this package, like expand the range of available explainers and comparison techniques, and as well enhance compatibility with existing machine learning libraries. So you're welcome to contribute to this open source package.
Compare the results of your options based on standard deviation. You calculate the standard deviation based on those three folds.
Three folds was an example. You can, it's like hyperparameter, you can choose 5, 7, and more.
Because standard deviation even from 5 or 7 samples is not a very robust